Welcome back to another fantastic lesson. Before we start lesson 4.2, which is on the mean value theorem and Rolle's theorem, I wanted to take a one question warm up here to recap what we did yesterday with closed interval method. So here it says find the absolute max and min values. Here's the interval. Now most of the time if this is on a common exam, they won't tell you to use the closed interval method. So really from here on out, if you see any questions involving finding the absolute max or absolute min, we're going to be applying the closed interval method. So try to remember that for any problem that you see with these questions. So remember the closed interval method is really, first we got to find the critical points of this function, which stem from the derivative. So notice we're going to have to use a product rule here. So if I did the first times the derivative of the second, now think of that term as negative x squared over 8, or that exponent could be easier looked at as negative 1/8 x squared. Because if you do the derivative of the second, I don't want you to have to do a quotient rule for the exponent. So the derivative ends up being e to the negative x squared over 8 times the derivative of that exponent, which in this case would end up being negative 1/4 x. And then remember the second part of the product rule, which would then just be plus the second function times the derivative of the first, which is just 1. So we're trying to solve for when this is 0 or where this is undefined, and this one's kind of a little tricky. So let's look at maybe a GCF between the two terms, because again, you're setting this equal to 0 and trying to solve. So notice that we do have an e to the negative x squared over 8 involved with both of these terms. And if I simplify that first term, if I expand it out or factor it out here, that I'd be left with negative 1/4 x times x, which ends up being negative 1/4 x squared. And then I have to have a placeholder of 1 for that second part. So remember, critical points is when it's 0, and in this case, there is no value that makes this outside 0. So we don't yield any there, but we might yield a couple here. So if I set that inside equal to 0 and solve, subtracting 1, multiplying by negative 4 gives me x squared equals 4, and then if I factor that, don't forget, if I take the square root of both sides, don't forget plus or minus 2 there. So we have two critical points, plus or minus 2, and so now we're at the stage of setting up our big table. So remember our table is we test the critical points, which are at 2 and negative 2, and then we also test the endpoints, negative 1 and 4. Now since this is a unique function here, we're probably going to get some decimal answers, which is fine. Just make sure you remember 3 decimal place rule. So you'd enter all these into, remember we're entering them into the original function of y, not the derivative. So I used my table feature, I put this under y1, the function, and then I used my table ask feature to get those outputs pretty quick. So when I entered these in, I got 1.213 for 2. I got negative 1.213 for negative 2. And if I sub in negative 1, I got negative 0.882. And then lastly, 0.541. And so off my list, even though they're decimal answers, which are fine, looks like this one ends up being the absolute max, and then this one would be the absolute min. So remember to have that statement in the end. So we'd say there's an absolute max at x equals 2, and then absolute min at x equals negative 2. So a little review from yesterday before we move on to today's stuff. Before we start today's stuff, I want you to do a little investigation like yesterday. If you can, draw your coordinate plane. Here's 2 points that actually specifically want you to plot. So negative 2, 2, and 3, 2. And then again, I want you to sketch a continuous function over that interval. So it's got to be continuous, no breaks. And it's got to be a function, so it's got to pass the vertical line test. But take a moment and see if you can draw this scenario out. So here's the 2 points. I plotted 3, 2, and I plotted negative 2, 2. And a lot of you might have just quickly done the connecting boom. They're just a straight line, which is fine. or some of you might have had some creativity and had some waves in there, but remember it's got to pass the vertical line test. But no matter how you drew it, what Rolle's theorem says, which is our first theorem of 2 today, it says no matter how you draw a continuous function between two endpoints, specifically that have the same output, if you notice, that there's at least one place where the derivative is 0. And so notice when I drew it here, there was a couple places there. So what Rolle's theorem says is if your outputs are the same, so that's something that you have to check, that the outputs are the exact same, then there exists a critical point or a max and min value between there's at least 1 or 2. And so really taking the derivative, setting it equal to 0 is going to help you find those x values. So here's what Rolle's theorem officially states. It says, again, you have to have a function. Number 1, it's got to be continuous, and this is step 1, so again, it's like a 3-step process. But step 1 is you have to state the function's continuous. How do we know that? Well, if it's a polynomial, it's continuous. If it's a rational function, it's continuous. Basically, any function is going to be continuous about its domain, and specifically over that interval there. The second part is stating that it's differentiable. And these two things are really just statements that have to be present first before you're to check the outputs that they're the same. And once there is the outputs that are the same, then you can jump ahead, lastly, to taking the derivative, setting it equal to 0, and finding those places where there's a max or min point where the derivative is 0. We can state that functions are continuous, basically of that theorem a long time ago that probably not many of you remember. But in chapter 2, we looked at a theorem that said all functions are continuous about their domains. And so that's why we can state that it's continuous. We don't have to prove it at all at this point. It's just a statement that the function's continuous and it's differentiable over that interval. So here's sort of a graphical interpretation again of what Rolle's theorem says. It says estimate the values of C for which the conclusion of Rolle's theorem is true. So here's my function. And remember what Rolle's theorem says, and notice the outputs are the same here. So that checks out, and it is continuous function, and you're able to find the derivative throughout the whole graph, so it is differentiable. So now if you notice when the derivative is 0, you can kind of estimate on the number line here where that happens. It looks like here's where the max point there, so roughly maybe about 2.7-ish would be 1 point. It looks like roughly at 10 would be another place where the slope is 0, and then also looks like roughly at 13 or 13.1 is where the derivative would be 0, 2. Now let's take a look at how to apply it with a function given. So here it says verify hypotheses of Rolle's theorem are satisfied for the function over that interval, and then find those values of C. So notice a lot of times they will kind of hint to make sure you remember to write down those first 2 hypotheses. And so we can say that since f is a polynomial, then f is continuous and differentiable. But you have to state that first before we apply the third part of Rolle's theorem, which says the outputs have to be equal. So let's test if f of 0 equals f of 3. Well, if I sub in 0 for the polynomial, you're just left with the constant term of 2 there. Next, let's sub in 3. So if I sub in 3, it looks like I get 27 minus 9, which is 18, and then minus 18 plus 2. Looks like I do also get 2. So since the outputs are the same, then and it's differentiable and continuous, then I can jump to stating finding the derivative and set it equal to 0. So in this case, it would be 3x squared minus 2x minus 6. And for this one, I don't believe it's actually factorable, so looks like we can use the good old quadratic formula. But in all honesty, if you showed that you setting this derivative equal to 0, you can use your calculator and do second trace 0 there to find the 2 values. Just make sure you remember 3 decimal places. But if I applied the quadratic formula here, opposite of b plus or minus the square root, my b term squared minus 4 times my a times my c, all over 2 times my a. I get 2 plus or minus the square root of, looks like 4 plus think I get 76 underneath, and then all over 6. And if you wanted to break down the square root of 76, I think it becomes 2 square roots of 19, because 76 is 4 times 19, and it's all over 6, and you can reduce both of the 2's up top, so it becomes, if I cancel a 2 out of each term, it'd be 1 plus or minus the square root of 19 all over 3. And so I believe if you did second trace 0 instead, one of the answers is negative 1.119, 3 decimal places. And then the other one is 1.786, it looks like. So these would be my 2 values that satisfy the conclusion of Rolle's theorem. So I want you to try one. So make sure you remember all steps of Rolle's theorem by stating the hypotheses first before you show the outputs are the same, and then work with the derivative equal to 0 to solve for x. So if we continue with Rolle's theorem, the first thing is we got to state the hypotheses, so simply stating that f is continuous and differentiable over that interval, and a lot of times they will be for these cases, so it's just, again, a statement. So we stated that. Second step, remember, is stating that the outputs are the same. So if I sub in 0, looks like I get 0 back. If I sub in 9, I get the square root of 9 minus 1/3 times 9, which is 3 minus 3, which is 0. So there, the outputs are the same. So now, since the outputs are the same, we're jumping right to finding the derivative, setting it equal to 0. So the derivative here would be 1 over 2 square roots of x minus 1/3, and you're setting that equal to 0 and trying to solve. So if I were to solve this one, you could do common denominator work if you want, but notice I can add that 1/3 over. So it becomes 1 over 2 square roots of x equals 1/3, and since I have a fraction equals a fraction, I can cross multiply and try to solve for x. So that means 2 square roots of x equals 3. And if I divide by 3 or divide by 2 to both sides, and getting rid of that square root, I would square both sides, and I believe I get 9/4 in the end, which would be my answer. And a good way to check is you could graph the derivative again and see that it crosses at 9/4, or you could graph the original function and see that that's a max or min at that 9/4 value. So the last theorem in this lesson is what's called the mean value theorem. So just like with Rolle's theorem, if we have 2 points, now in this case the outputs don't have to be the same. But what the mean value theorem is that if you have a continuous and differentiable function between the two, so something like this, that what Rolle's or MVT says is that whatever the slope of the secant line is, so the slope between 2 points, there's at least one place where the tangent slope is parallel. And so if you notice, roughly about like negative 1.8, it looks like that would be where the tangent would be parallel. And it looks like somewhere, and if I drew it a little bit more accurate, we might see a little bit better, but somewhere a little past 1, it looks like it also is parallel to that line. So we use a formula. But before we get to the formula, let's kind of look at the graphical interpretation of this again. So here it says estimate the values of C for which the conclusion of MVT is true. So notice we have different outputs, doesn't matter. But if I were to draw a secant line through those 2 points, it looks like there's potentially 3 places that there might be a tangent slope that's parallel. And so if I were to estimate, it looks like somewhere right about here, so maybe 3.1-ish, maybe, that's where that happens. It looks like it might be parallel just shy of the max point, so maybe something like 8.7 or somewhere around 9. And it looks to me like a little past 13, so maybe like 13.1 looks to be where that might be parallel to the slope of the secant line. So we do have a formula to use, and there is, again, specifics that we have to state first before we apply the formula. So notice again, just like with Rolle's theorem, you have to state that it's continuous and differentiable, and it's just a statement. But we don't have to show that the outputs are the same because they will be different here. So the next step would be jumping right to that last part, which is our formula that we're going to use for MVT. And so if you think about this graphically, remember the derivative, that's the slope of the tangent line. And then this represents slope of the secant line, slope between 2 points using average rate of change. And so it makes sense that if we're trying to see where they're parallel, that'd be where they're equal to each other. So if we take a look at this example below, it says verify the hypotheses, or verify the function satisfies MVT, and then find those values. So again, we have to state that f is continuous and differentiable. And again, it's a statement. Done, check. It's a polynomial. And so right away, we're taking the derivative. And so if I apply this formula, the derivative of the left in terms of c, and it doesn't matter if you use c or x. Usually they're required to use c, but if I took the derivative, it ends up being 6c plus 2 equals, and then it'd be f of 1 minus f of negative 1 all over 1 minus a negative 1 on the bottom if I applied the average rate of change formula. And so on the left side, I still have 6c plus 2. But on the right side, we're going to get a numerical answer for this. And so if I sub in 1 for x, it looks like I get 10. If I sub in negative 1 for x, let's see, I get positive 3, minus 2 is 1, plus 5 is 6, over 1 minus a negative 1, which is 2. So I get 6c plus 2 equals 4 over 2, which is 2. And to solve for c, I would subtract 2 and divide by 6. So it looks like c equals 0 would be that value for which the slope is parallel to the slope of the secant there. So c equals 0 is my answer. So see if you can try one of these. It says verify the function. So again, remember the hypotheses. State both of those first before you take the derivative and set it equal to the average rate of change this time. Might be a little bit challenging to try to solve for x here, but try your best. So remember, you can pause the video, work this out. In a few seconds, we'll look at our answer. So let's check our answers here. So the first step, don't forget, just statement, f is continuous and it's differentiable. This is a exponential function, so really the domain is all real numbers here. And so we stated that, check. Now we're taking the derivative and setting it equal to the average rate of change. And so here's my formula, which common exam wise, usually there's some evidence of formula points. Same with our quiz, we want to encourage you to show the formula first before you take the derivative work and have that average rate of change work on the side. But the derivative of this function would be e to the negative 2x times the negative 2, because that's a chain rule there. And then if I sub in my bounds here and evaluate, I get negative 2 e to the negative 2x on the left side. If I sub in 3 for the function, I get e to the negative 6. And if I sub in 0, I get 1 over 3. And so you're trying to solve this. Here we're probably going to get some kind of decimal answer. In fact, it's okay to have decimal answers. So maybe get a decimal answer for what the right side is going to be there. And so in doing that, I get negative 0.333 if I rounded 3 decimal places. So to solve for x, I would divide by negative 2, which gives me e to the negative 2x equals 0.166. And then solving for exponential functions, remember, a little prerequisite skill, to get rid of or to solve for an exponent, we take the natural log of both sides. That allows me to bring this down in front. And what I'm left with, notice natural log of e is 1, so my answer for x is going to be really whatever the natural log of 0.666 is, or 66 is, and divide by negative 2. So if I take the natural log of that answer divided by negative 2, I get a final answer of 0.897. Now, with any of these, and I should have mentioned this before, you always want to double check that that value is in that interval. So notice 0 to 3 was my interval. 0.897 was in that interval. So if you find an answer using MVT or Rolle's theorem that is outside the interval, you wouldn't consider that part of your answer. So there is some group work out there if you want to, again, totally optional, but if you get done with the homework early and you want to check that out in the meantime, these are kind of your typical common exam style questions, so it is worth checking out, but there's some real world applications to it, as well as just applying some function stuff to it. And some of these are a little bit trickier to work out, but you can try your best and look at both of those group works out there that I have in Canvas. So that concludes our lesson. The homework is pretty short because these problems do take a while to kind of work out, but it is just focused on MVT and Rolle's theorem. Later this week, we're going to have a quiz on just these last two lessons, so on the closed interval method and on MVT and Rolle's theorem, so start preparing yourselves for that and look for some of the review materials that I'll have for you in tomorrow's lesson. Hopefully enjoy your night.